We have been studying the synchronization transient of a synchronous machine connected to an infinite bus. What we saw last time was that you can have a near bumpless synchronization of a synchronous machine to an infinite bus, which is essentially a fixed voltage source. The machine locks on to the frequency of the infinite bus in case it is synchronized well. Now, the thing we noticed last time was that if the speed of the machine initially is almost the same as that of the infinite bus, and at the instant of the interconnection, the voltage, open circuit voltage of the generator, the voltage phasor you can say, is practically the same as the infinite bus voltage phasor, then you get a kind of a bumpless transfer. Okay. Of course, you can't get in perfect transfer without transients, it is practically not possible. There will be some transient because you can't do this match which I mentioned some time back exactly. So, what you really see is that when you connect a synchronous machine to an infinite bus, you do get a small synchronization transient. Most notably, you notice a kind of a what is known as a swing mode or a low frequency oscillation, which usually damps down, and that really, after that, the synchronous machine is in synchronism with the voltage source. Thereafter, if you increase the mechanical torque to the synchronous machine, you find that the machine transfers power from itself to the voltage source or the infinite bus. So, what you notice there of course is that as you go on increasing the mechanical power, you will find that the angle delta increases. Okay? And in fact, there comes a point after which if you try to increase the mechanical power, the synchronous machine in fact loses synchronism. There is it kind of fails to reach a steady state in case you go on increasing the mechanical power beyond a point. Okay. Of course, the important thing is that we had in fact seen precisely such a transient in one of our lectures. In fact, the first lecture I had shown you a small demonstration clip. It will be good to revisit that clip. You can go back to the first lecture and see that clip. That is precisely what we have tried to simulate in the 21st lecture. That is a synchronous machine connected to a infinite bus, and thereafter we go on increasing the mechanical power to a point at which it loses synchronism. One of the things which we did not do when we increased the mechanical power was or the mechanical torque to the synchronous machine was that we did not increase the field voltage simultaneously. In fact, a synchronous machine tends to lose synchronism very easily in case you try to load it without a concurrent increase in the field voltage. Okay. So, what we will do in this lecture is we will first of all revisit this earlier transient in which we first give a small step, we first synchronize the machine, then give a small step in the mechanical power of 0.25 per unit, and then we try to increase the mechanical power right up to its rated value of 1 per unit, and there we do not increase the field voltage, we will see that it loses synchronism. Thereafter, we will redo this simulation with by increasing the field voltage concurrently, that is at the same time as we we increase the field voltage simultaneously, perhaps simultaneously is a better word. We increase the field voltage simultaneously along with the mechanical torque. You will find that under such circumstances the generator is able to supply the rated power to the infinite bus. Okay. Now, one small clarification, of course, I hope you did not miss it last time, was that when we are simulating the equations of a synchronous machine, we are neglecting the stator transients or the stator flux transients. That is, we have replaced d psi d by dt and d psi q by dt by 0. The reason is of course that the transients associated with these states psi d and psi q are very fast. So, what we have done essentially is replace the differential equations which relate the psi d and psi q fluxes by algebraic equations. One thing you should note here is that an implicit thing is that when I am making this assumption, I am really interested in the slower electromechanical transits. That is why I can do without the psi d and psi q differential equations, replace them in fact by the algebraic equations, okay, and still get a reasonably correct result. Okay. Now, you may ask that, well, why do I do it anyway? You can just as well keep the differential equations corresponding to psi d and psi q. The reason why, of course, I have done that is, if I